Enthalpy, entropy, and Gibbs free energy. In this particular chapter, we're going to talk a little bit about some values that are involved in chemical reactions. And we're going to need to have a table to read these values. So I want you to get your books, and you're going to open up to the appendix at the back of the book, page A20, and we want to look at that table. We've seen it before. It lists substances and tells you the state of the substance. And it gives you the delta H of formation, or the enthalpy of formation, of 1 mole of a particular compound from its elements. And the units are kilojoules per mole. We've got a second column, which is a delta G value, and a third column, which is an S value, and we're going to be looking at those columns of numbers as well in this section. So let's talk about the first law of thermodynamics, and this is a review from earlier in the year. And the first law of thermodynamics states that the amount of energy in the universe is finite. In other words, energy can't be created or destroyed. It can be converted from one form to another, but the total amount of energy in the universe is a constant. Energy can be expressed in the form of heat or work, and for our purposes, we're going to be dealing with the heat flow during a chemical reaction, or the enthalpy changes that take place during chemical reactions. When we talk about enthalpy, it's the heat change associated with the chemical reaction, and we can calculate that value for a reaction by taking the sum of the enthalpy of formation of our products minus the sum of the enthalpy of formation of our reactants. So we look at a balanced equation, we figure out how many moles of each substance there are in that balanced equation, look up the delta H of formation values for those substances, plug them into the equation, and we can decide what the delta H value for a reaction is. Remember that if the delta H of reaction is a negative value, it tells us that a process is an exothermic process. So energy is being released. Our products will have less energy than our reactants had. And if our delta H of reaction is a positive value, we're looking at a process that's an endothermic process, which means that energy is being added into the particular process, so our products will have more energy than our reactants had. So here's an example of a problem. Again, this is something that we've seen in earlier chapters, so we should be able to do this using the values on the table. It says calculate the enthalpy change, or our delta H value, for the following reaction. So we have gaseous methane reacting with gaseous oxygen to produce gaseous carbon dioxide and liquid water. We look at the balanced equation. That tells us how many moles of each substance we need in that balanced equation. We're going to look up the enthalpy of formations for the substances in the reaction, multiply those values by the coefficient in the balanced equation, and then take the sum of the products minus the sum of the reactants, and that'll tell us what the delta H of the reaction is. So I'm going to give you a minute. Look at the table, find the values, plug them into your equation, and see what you get for your delta H of reaction. All right, so we're going to take 1 times the enthalpy of formation of carbon dioxide, which is negative 393.5. We're going to add to that 2 times negative 286, which is the enthalpy of formation of liquid water. And then we're going to take 1 times negative 75, which is the enthalpy of formation for methane, plus 2 times 0, which is the enthalpy of formation of oxygen. And remember that free elements have an enthalpy of formation value of 0 because they're not compounds being formed from their elements. We'll plug those values into the calculator, and we're going to get negative 890.5 kilojoules, which we can then plug into that equation on the product side, since it's energy that's being lost. And that tells us that the reaction is an exothermic process. Now, let's look at a new topic. We're going to look at the second law of thermodynamics. And when we deal with the second law of thermodynamics, it's dealing with the entropy of a system. When we talk about entropy, we're dealing with the disorder in a system. And matter tends to go towards more disorder. So entropy is the degree of disorder in a system. We're going to represent it with the symbol S. And matter tends to go from a more ordered state to a less ordered state. So matter tends to go towards a greater degree of disorder. So let's look at a couple of examples. Here we've got liquid water that we're decomposing into hydrogen gas and oxygen gas. Since it's a decomposition process, we're increasing the disorder in the system and the entropy would go up. If we look at liquid water going to gaseous water, we're looking at an evaporation process. Liquid molecules are more ordered than gaseous molecules are. So in this case, we're increasing the entropy of the system, or we're increasing the disorder of the system when our substance goes from a liquid to a gas. If we were to look at solids, solids are much more ordered than liquids, and liquids are much more ordered than gases. So if we talk about entropy, gases have much more entropy than liquids or solids have because there are no intermolecular forces holding those particles in a set arrangement. If we go from solid to ions in solution, if we take a solid and dissolve it into water, we're increasing the entropy again because those ions are free to float around in the solution. If we look at bonding, ionic bonding has a greater order to its crystalline structure. Covalent bonds are a little bit less ordered, and metallic bonds are the least ordered or have the greatest entropy because, again, remember that the metal atoms within a metallic bond have the ability to flow through that sea of electrons. The entropy increases as we increase the number of particles that are in a particular sample because there are more positions where those particles can be. The disorder goes up. And entropy increases as the molecules become more complex. When we go to calculate the entropy change for a particular system, we can estimate whether or not the entropy is going up or the entropy is going down by comparing the reactants to the products, but we can also use the table in the book to calculate what that value would be. And we do that in a very similar way to the way we calculated the enthalpy change for a particular reaction. We're going to take the sum of the entropies of our product and minus the sum of the entropy for our reactants. Again, the values on the table this time are in terms of joules per Kelvin mole. We're going to have to multiply the values by the coefficient in the balanced equation. And also entropy is a temperature dependent value. So what we want to do is use our table in Appendix A20. This time we're going to look up the entropy values. We're going to multiply them by the coefficient in the balanced equation, add up the sum of the products minus the sum of the reactants, and calculate the entropy change for this particular process. So I'm going to give you a minute to go through and do that calculation. So when we plug those values in, we'll have 1 times the entropy of carbon dioxide, which is 214, plus 2 times the entropy of liquid water, which is 70. We'll add all that together. That's the sum of our products. We'll take 1 times the entropy for methane plus 2 times the entropy for oxygen and add that all together, and that'll be the sum of our reactants. We'll take our products minus our reactants and get our value. And we get a value of negative 270 kilojoules of entropy change. And when we look at that, it makes sense that the value is a negative value because we're going from gases to gases and liquids. Last, we want to talk about Gibbs free energy. And a Gibbs free energy value is going to help us to predict whether or not a process is spontaneous or not. If we calculate our Gibbs free energy value, our delta G value, and the value is negative, that means that the reaction is a spontaneous reaction in the forward direction, okay, from left to right or towards our products. If our delta G value is calculated to be a positive value, it means that the forward reaction is not spontaneous, or the reverse reaction is spontaneous. If delta G equals 0, then the system has reached equilibrium and the rate of the forward reaction equals the rate of the reverse reaction. We can calculate our delta G value for a particular reaction in a similar way that we calculated our entropy and our enthalpy. We'll take the sum of the products minus the sum of the reactants. So again, reference the table on page A20, plug in your values, and calculate your delta G value. All right, so when we plug all those values in, we should be getting negative 817 kilojoules for our answer, which tells us that this reaction is spontaneous. And when we think about the reaction, it is a combustion reaction. And we know that once we initiate the reaction, we have that activation energy met. Things burn on their own. Now, the last thing we want to look at is the Gibbs free energy equation, which is delta G equals delta H minus T delta S. And this is a way that we can relate enthalpy, entropy, and Gibbs free energy. So if we look at this particular table, it's a summary of the equation. If delta H is negative, that means it's energy favored. If delta S is positive, it means that its entropy is increasing. So that's favored. Our delta G value will always come out to be a negative value, which tells us that the reaction is always spontaneous. If delta H is a positive value, that means it's not energy favored. If delta S is negative, it means that we're decreasing the entropy, which is not favored. And if we plug those values into the equation, the delta G value will always come up to be positive, which means that that particular set of conditions will never be spontaneous. If we have a reaction that's endothermic and increases its entropy, it depends on whether the delta H or the delta S value in the expression is the larger value. If the temperature is high, the delta S times T will be a bigger value than your delta H, and you'll get a negative delta G, which means that the process is spontaneous. If we're at low temperatures, though, the delta H would be the larger value, and you get a positive delta G, which means that the reaction would not be spontaneous. And in the last set of circumstances, if delta H is negative, that means it's exothermic and favored for enthalpy. If delta S is negative, that's not favored because the entropy is decreasing. The only time the system would be spontaneous is at low temperatures.